Yesterday we did those open-ended box problems, finding the maximum and solving them, and in my opinion that was a very cool question and a very neat way to solve a maximum problem. It was interesting, and I can see the benefit of it, because if you had cardboard and you were making boxes to ship things, you would want to know what's the biggest volume possible. Today we're going to do a question that is of no use whatsoever, has no real practical. Well, the situation is not practical at all. Like, read this question. Clara and 3 friends were born on March 11th. Leslie is 5 years younger than Clara. Mike is 2 years younger than Clara. Thomas is 3 years older. And on March 11th, 2011, the product of their ages was 61,136, greater than the sum of their ages. How old is Claire? Well, you would probably just ask her, right? And if you knew this number, 61,136, it'd be like, who does that? Who multiplies ages together? Nobody. So this is an example of a question that is just made so that you can do math. There is no other practical purpose to this problem. But it still gets at some important math concepts. So some of the important math concepts that we have to do is, how do we take a word problem and put it into an equation? Well, first of all, we need to define something as x. Since everybody is being compared to Clara, it makes sense that we say Clara is x years old. Mike is 2 years younger than Clara. So that would be x minus 2. Thomas, 3 years older, x plus 3. And am I missing anyone? Leslie. Leslie is 5 years younger, so that'll be x minus 5. So those are the ages. And now this last or second last sentence, the one with the 61,136, that's supposed to give us enough information to write an equation. The product of their ages was 61,136 greater than the sum. So I'm going to start it out by putting product on one side, just in words, and sum on the other side. Now, they're not equal. But I'm starting off with my equation with product on one side, sum on the other, and saying I know that they're not equal because it says that the product was 61,136 greater than the sum. So how do I put that 61,136 to make them equal? What would I have to do? Well, part of what I like to think about is which one's bigger. Right now, which one's bigger, the product or the sum? The product is bigger. So this sum side is less. So if we wanted to make them equal, we would have to add the 61,136 to that side. Now, writing this with x's is the next part. What does it mean when I say a product of their ages? It means I'm going to take all of their ages and multiply them together. What would that look like? X times x minus 2 times x plus 3 times x minus 5. Equals the sum. If I add all of those up, if I add up my x's, would you agree that's going to be 4 x's? If I add up the numbers, negative 5 plus 3 is negative 2, minus 2 is negative 4. And then I still have the plus 61,136. And we have to solve this. Okay? If you tried to solve this by hand, it's going to be long and tedious and not very much fun, because you would have to multiply all of this out on the left side, then combine like terms with the right side, make it equal to 0, and then retry to factor it. And just quick mental math says that the last term, if once I combine these, those will be the only constant terms, I'm going to get 61,132. So those will be the factors you're going to have to try with the factor theorem to factor it. Obviously, it would be a calculator question, so if it's a calculator question, we may as well use our graphing calculator to its best of its abilities to solve this. And I'm going to show you two ways that you could use your graphing calculator to solve it. And both have advantages and disadvantages. Okay? I'm going to do the one that I think in this example has the advantage, but more often the other technique is going to have an advantage more often. So in this one, what I'm going to do is I'm not going to multiply this out, but I'm going to move everything over. So if I move the 4x over, it'd be minus 4x. This would be 61,132. If I move that over, it'll be minus 61,132. And I'm going to make one side equal to 0. If you make one side equal to 0, what you can do on your graphing calculator, clear this out, type in the equation x minus 2 is it x minus 2, x plus 3, x minus 5? Okay, good. Minus 4x minus 61,132. So what this does is we can now hit a zoom. I'm going to just do zoom fit to get something crazy as my initial graph and see what it looks like. Wonderful. And this graph should tell us almost nothing, and it does tell us almost nothing. But we have to ask ourselves, what are we looking for? When I type this into y equals, I basically wrote y equals all of this. What am I looking for? I'm looking for the answer to this question is when y is equal to 0. What is that called on a graph when y is equal to 0? That's our x-intercept, right? You've been trained that so well, it's almost like a reflex. Y equals 0, x-intercept, right? How do you find the y-intercept? Put x equals 0. It's like a reflex, and that's good. That's one of those math teachers, we want you to have that reflex, to think of that quickly. So I want to find an x-intercept. The zoom fit provided a terrible window. And this is why in this example, I think this technique is going to be easy, because I'm going to go to my window. I'm going to say to myself, I'm solving for x. What is x? X is Clara's age. So because I know the context of the problem, what values seem reasonable? Well, I'm going to start at -1 just so I can see my x-axis. It doesn't make sense to go further into the negative, because she can't be -15 or something like that. Also, for x max, I'm not going to put 1,000. I'm pretty sure Clara is not 982 years old. Okay? Probably, okay, I'm going to put 100 just because she could be that old. And if nothing shows up, we could go older than that. But I'm also saying, oh, this is a high school textbook. They're probably going to put an age that's somewhat around your age. So I'm going to start with 100 and see what goes from there. We need to see our x-axis. It really doesn't matter anything other than that. So I'm just going to go from -10 to +10 just to make sure I see my x-axis. Chances are I'm not going to see much of my x to the 4 graph in this, but I'm just concerned with finding an x-intercept. So when I hit graph, our question is, can we see an x-intercept somewhere? Yeah. Looks like it's right there. So as far as finding that, now we go second, calculate we need to find x-intercept, which is number 2, a 0. We need to be on the left of that and the right of that. Now, that line is going straight up and down. If I arrow back and forth, I can't see where my cursor is whatsoever. I knew that I went to 100. Maybe if I want to go to my window, I can change my x scales by 10. That tells where those ticky marks are. That might help me estimate it a little bit better. Does it look like it's between the ages of 10 and 20? So now when I want to find my 0, so I'll go back to calculate number 2 to 0. A left bound 10 seems reasonable. 20 seems reasonable for the right bound. Enter our guess, and we find out that Clara is 17 years old. Oh, I want to point out something on there. Notice we have 17 for x. Notice our y is 1.6e minus 8. Some of yours might say 0. Some of yours might say different things. What the calculator does when it figures this out is it says we want y to be 0, and we're going to get closer and closer to 0 until we feel it's close enough. And it felt it was close enough. 1.6 e to the minus 8 is scientific notation. It means decimal 0.000000016, which is really, really close to 0. But just to be aware that if your calculator ever gives you numbers with an e like that, you have to think in scientific notation. So we know that Clara is 17. We can now say, how old was Clara? 17. How old were each of these friends? Well, this 15, 20, 12. And we get each of the ages. Practical question? By no means no. But is this skills-wise things that are important? Yes. How to use a graphing calculator to solve something? The way that we did it first was we moved everything over to one side and made it equal to 0. That means that we could find an x-intercept. I'm going to show you another way that you often solve these with your graphing calculator. In this case, it doesn't work as well, but usually it works better.
How did you know to put your left bound and right bound at like 10?
So once, how did I know to go 10 and 20 for my left? Once I made those ticky marks, going 10 each, I knew that 10 was to the left and 20 was to the right. I could just eyeball it. But if you use 10 and 40, that would be fine. If you looked at this one and said, well, for sure 0 is to the left and 100 is to right, it'll work as well. So the other way is you don't have to do any rearranging. You have your original equation, and this side you put into y1, and this side you put into y2. The nice thing about this technique is you have less chance of making an arithmetic or a silly mistake because you don't have to change anything. So I'm going to go back to my calculator. I'm going to go to y equals. In y1, I just need to delete this extra stuff. And in y2, I mean, you could simplify it, but you wouldn't even have to. The calculator will do that for you. So if I write it exactly as it is, 61,136, and then hit graph, it's going to draw two graphs. Mine are color-coded, one in blue, one in red. One in red. One in red. Okay, so we don't see the red one whatsoever. And we need to find out where these two graphs intersect. So this is part of the problem with this method, is the other method, we could at least say, I need to find an x-intercept. Some age between 0 and 100 seems reasonable, and it was easy to find. This one, I need to find an intersection, but x should be between 0 and 100, so that's still reasonable, but I can't see anything else. So then you could be playing around with your window for a long time. So you might try, well, let's see what zoom fit does. Oh. So we got a line right along the bottom and the blue one going across. It might be that those intersect, but it's very hard to tell from this graph as well. Checking out our window, our Y-min started at negative 50 and went up to, oh nice, 95 million. So going back to our graph, we sort of think, well, maybe I could solve this. Now that they're both showing up, you could try second graph, and when you have two graphs, you want to find out where they intersect. So you push enter on one, enter on the other, and enter again, and maybe it's going to give us our answer. In this case, it does. It did find out 17, even though the window was terrible. So the hard part about this second technique is finding a window that fits. I think if, in this case, if we went up to 70,000, I think this shows up as a solution a lot nicer. Where's our red graph? Maybe this is bad. Oh, there it is. Wait for it. And that really shows the intersection of those two a little bit better. But the hard part in this technique is setting up your window so you can see your two graphs cross. So sometimes it's going to be nicer to set things equal to 0 and find an x-intercept. And sometimes it's going to be nicer just to put one equation in y1, one equation in y2, and then you can go second, calculate number 5, find out where they intersect. The nice thing about this, you don't need to know left and right bounds. It just says first curve, push enter, okay. Second curve, push enter, okay. Guess. Here? I don't know why it gets you to guess. And it finds the same answer the same way. Okay, questions you can do for this one are 7 and 8.